Sound is a longitudinal wave that is created by a vibrating object, such as a guitar string, the human vocal cords, or the diaphragm of a speaker. Moreover, sound can be created or transmitted only in a medium such as a gas, liquid, or solid. As we will see, the particles of the medium must be present for the disturbance of the wave to move from place to place. Sound cannot exist in a vacuum. To see how sound waves are produced and why they are longitudinal, consider the vibrating diaphragm of a speaker. An electrical signal, such as that created by a microphone, is transmitted to the speaker, causing the diaphragm to vibrate. When the diaphragm moves outward, it compresses the air directly in front of it. This compression causes the air pressure to rise slightly. The region of increased pressure is called a condensation, and it travels away from the speaker at the speed of sound, which is 343 meters per second in air. The condensation is analogous to the compressed region of coils in a longitudinal wave on a spring. After producing a condensation, the diaphragm reverses its motion and moves inward. The inward motion produces a region known as a rarefaction, and the air pressure is slightly less than normal. The rarefaction is similar to the stretched region of coils in a longitudinal spring wave. Following immediately behind the condensation, the rarefaction also travels away from the speaker at the speed of sound. The process repeats, forming multiple cycles of a longitudinal wave. As the wave passes through a specific region, the colored dots attached both to the spring and to an air molecule execute simple harmonic motion about their undisturbed positions. The colored arrows on either side of the dots indicate that the simple harmonic motion occurs parallel to the line of travel. The wavelength lambda is the distance between the centers of two successive condensations. Lambda is also the distance between the centers of two successive rarefactions, or any other repetitive point on the wave. If a sound wave is not confined to a tube, it will spread out in space. In fact, if the sound were created by a vibrating sphere, the wave would propagate radially outward in all directions. When condensations and rarefactions arrive at someone's ear, they force their eardrum to vibrate at the same frequency as the speaker diaphragm. The vibratory motion of the eardrum is interpreted by the brain as sound. It should be emphasized that sound is not a mass movement of air, like the wind. As the condensations and rarefactions of the sound wave travel outward from the vibrating diaphragm, the individual air molecules are not carried along with the wave. Rather, each molecule executes simple harmonic motion about a fixed location. In doing so, one molecule collides with its neighbor and passes the condensations and rarefactions forward. The neighbor, in turn, repeats the process. The red arrows indicate the directions of these oscillations in different parts of the spreading wave. Each cycle of a sound wave includes one condensation and one rarefaction, and the frequency is the number of cycles per second that passes by a given location. For example, if the diaphragm of a speaker vibrates back and forth in simple harmonic motion at a frequency of 1000 Hz, then 1000 condensations, each followed by a rarefaction, are generated every second, thus forming a sound wave whose frequency is also 1000 Hz. A sound with a single frequency is called a pure tone. Experiments have shown that a healthy young person hears all sound frequencies from approximately 20 to 20,000 Hz. Sound can be generated whose frequency lies below 20 Hz or above 20 kHz, although humans normally do not hear it. Sound waves with frequencies below 20 Hz are said to be infrasonic, while those with frequencies above 20 kHz are referred to as ultrasonic. Some species of bats, known as microbats, use ultrasonic frequencies up to 120 kHz for locating prey and for navigating, while rhinos use infrasonic frequencies as low as 5 Hz to call one another. Frequency is an objective property of a sound wave because frequency can be measured with an electronic frequency counter. A listener's perception of frequency, however, is subjective. The brain interprets the frequency detected by the ear primarily in terms of the subjective quality called pitch. A pure tone with a high frequency is interpreted as a high-pitched sound, while a pure tone with a low frequency is interpreted as a low-pitched sound. For instance, a piccolo produces high-pitched sounds, and a tuba produces low-pitched sounds. Here we show a pure tone sound wave traveling in a tube. We can attach a series of gauges to the tube that indicate the pressure variations along the wave. The graph shows that the air pressure varies sinusoidally along the length of the tube. Although this graph has the appearance of a transverse wave, Remember that the sound itself is a longitudinal wave. The graph also shows the pressure amplitude of the wave, which is the magnitude of the maximum change in pressure measured relative to the undisturbed or atmospheric pressure. The pressure fluctuations in a sound wave are normally very small. For instance, in a typical conversation between two people, the pressure amplitude is about 3 times 10 to the negative 2 pascals, certainly a small amount compared with the atmospheric pressure of 1.01 times 10 to the 5th pascals. The ear is remarkable in being able to detect such small changes. Loudness is an attribute of a sound that depends primarily on the amplitude of the wave. The larger the amplitude, the larger the sound. The pressure amplitude is an objective property of a sound wave since it can be measured. Loudness, on the other hand, is objective. Each individual determines what is loud depending on the acuteness of his or her hearing. In summary, a sound wave is a longitudinal wave created by a vibrating object such as a speaker or vocal cords. Condensation is the part of the sound wave where the air pressure is higher than normal. Rarefaction is the part of the sound wave where the air pressure is lower than normal. Infrasonic sound waves have a frequency lower than that detected by human hearing, or less than 20 Hz. Finally, ultrasonic sound waves have a frequency higher than that detected by human hearing, or greater than 20 kHz.